12.2 Lesson 2, Integration of Vector-Valued Functions. Our objectives for today are 1. You will be able to integrate a vector-valued function. 2. You'll be able to find an antiderivative of a vector-valued function that satisfies a given initial condition. Before we look at an example for Objective 2, when we get to that, we would also look at the AB, calculus AB equivalent of that problem so that you understand the relationship between the problem that we'd like to look at for Objective 2 and what you've already done in calculus AB. Vocabulary, indefinite integral. When you have an indefinite integral, you're looking for an antiderivative. So you get a family of functions for your antiderivative. They differ by a constant of integration. When you're looking for a definite integral, you would use the fundamental theorem of calculus. You have limits of integration, and you get a number, or in the case of a vector-valued function, you would get a constant vector for the answer for a definite integral. And then we'll look at a differential equation. What do we mean by the general solution? If we have something called an initial condition, you'll have a particular solution. With differentiation, to find the derivative of a vector-valued function, you differentiated the vector-valued function on a component-by-component basis. When we found limits of vector-valued functions, you looked at each of the component functions. When we worked with continuity, you looked at each of the component functions. The same is the case for integration. So let's look at the definition of integration of vector-valued functions. And what you will see in this definition is that integration of vector-valued functions is done on a component-by-component basis. So if you have a vector-valued function, r of t is equal to f of t I plus g of t j, where f and g they are what we call the component functions. They're real-valued functions, continuous on the closed interval from a to b. Then the indefinite integral or antiderivative of the vector-valued function is found by finding the antiderivative of each of your component functions and multiplying by the respective standard unit vector I or j. The definite integral is found in the same way. To find the definite integral of a vector-valued function from a to b, you would find the definite integral of each component function from a to b, and then multiply by their respective standard unit vectors I and j. And number 2 is the same thing that we just looked at for number 1, but number 2 is for space curves, where you have an extra dimension, and you have an extra standard unit vector k. For space curves, the standard unit vector I would be, there's a third dimension. There's the x direction, the y direction, and the z direction. And the standard unit vector j would be this. And the standard unit vector k has an x component of 0, a y component of 0, and a z component of 1. We begin with example 5, find the indefinite integral, and we have our vector-valued function. The horizontal component function is f of t is equal to t, and the vertical component function is g of t is equal to 3. So, as we can see from how to find the antiderivative of a vector-valued function, we do so on a component-by-component basis. So let's take a look at this one step at a time. So we're going to have the indefinite integral of t dt, and then we're going to multiply that by the standard unit vector I, and we're going to add to that the indefinite integral of 3 dt, and we're going to multiply that by the standard unit vector j. So an antiderivative of t with respect to t would be t squared over 2 plus a constant of integration that we will call c sub 1. And then we have I. And then for the vertical component, an antiderivative of 3 with respect to t would be 3t plus a constant of integration that we will call c sub 2 To distinguish it from C sub 1, we call it C sub 2. And then we're going to multiply that by the standard unit vector j. Now here's something that you should note. We can now distribute the standard unit vector I to each of these two components, and we will also distribute it to the constant of integration C sub 1. We will do the same thing with the standard unit vector j, distribute it to 3t, and the constant of integration C sub 2. What happens when we do that? Let's bring our work to the top here. So we will have t squared over 2I plus C sub 1I plus 3tj plus C sub 2j. So we're going to have t squared over 2I plus 3tj plus C sub 1I plus C sub 2j. And this is what I'd like for you to notice. What you have here is just a constant vector. C sub 1 could be any constant such as 5 or 7 or negative 2. And C sub 2 likewise could be any constant, 0, 3, 7, negative 1/2, etc. So another way you can write the answer here is just writing t squared over 2I plus 3tj plus c, where c represents a constant vector. It would be what we had here. Now that you understand what we just went over, we could do example 5 in a more condensed way, as I'm about to show you now. So how do we integrate vector valued functions on a component by component basis? So you're going to write the indefinite integral of t dt plus, and then you have the standard unit vector I, plus the indefinite integral of 3 dt multiplied by the standard unit vector j. So in the next line, I'm going to find the antiderivative of t with respect to t, which is t squared over 2. But I'm not going to worry about the constant of integration because, as we saw with having done example 5 already, each scalar constant of integration, since each scalar constant of integration is multiplied by its respective standard unit vector I or j, when you take the combination of the scalar constants of integration multiplied by the standard unit vectors I and j and combine them, you get a constant vector. So we will just have plus c, our constant vector, instead of worrying about each scalar constant of integration and then doing it the way we saw with example 5 just a couple of minutes ago. So if you do that, then you just have t squared over 2I, and then you would find an antiderivative of 3 with respect to t, which is 3t, multiply that by the standard unit vector j, plus this constant vector of integration. And of course, that constant vector of integration, we saw it in the earlier version of example 5 when we did it the long way. And you can see that the constant vector of integration is, in fact, c sub 1I plus c sub 2j, where c sub 1 and c sub 2 are scalars, coming from each of these constants of integration of the individual component functions. So here we're looking at example 6, definite integral of a vector-valued function. So again, how do you find the definite integral of a vector-valued function? You do so on a component-by-component basis. So let's go ahead and take a look at how this is done. So we have evaluate the integral. It's a definite integral from 0 to 1 of the vector-valued function r of t, and we're integrating with respect to t. So here's the vector-valued function r of t. In fact, we have 3 components. This is a space vector. But it doesn't really change anything. You're just going to evaluate each of the component functions. You're just going to find the definite integral of each component function. So let's go ahead and look at how that's done. So our component function for I is is the cube root of t. So you can see that when you want to evaluate the definite integral of the vector-valued function, you're going to evaluate the definite integral of each of the 3 component functions. So here we have the definite integral of the cube root of t from 0 to 1 with respect to t, multiplied by the standard unit vector I. And of course, you can write the cube root of t as t to the 1/3. And then you have the definite integral of 1 over t plus 1 from 0 to 1 multiplied by the standard unit vector j. And then, of course, you have the definite integral of e to the negative t from 0 to 1 multiplied by the standard unit vector k. So all you need to do now is find an antiderivative of t to the 1/3. So you use the power rule for integration, add 1 to 1/3, you get 4/3, divide by 4/3, which is the same as multiplying by 3/4, and evaluate the antiderivative at the upper and lower limits of integration, and subtract. So that's using the fundamental theorem of calculus, and of course multiply by the standard unit vector I. So what's an antiderivative of 1 over t plus 1? It's the natural log of the absolute value of t plus 1. And evaluate that at 1 and 0. Subtract. And of course, multiply by the standard unit vector j. And here you have the antiderivative of e to the negative t, which is e to the negative t multiplied by negative 1. Evaluate the antiderivative at the upper and lower limits of integration and subtract, and multiply by the standard unit vector k. So once you've done that, you just go ahead and do what you're supposed to do, carrying out the steps from the fundamental theorem of calculus. So you get 3/4 I plus natural log of 2j plus 1 minus 1 over ek. And you will notice that the definite integral of a vector-valued function is a constant vector. 3/4 is a constant, natural log of 2 is a constant, and 1 minus 1 over e is a constant. So the definite integral of a vector-valued function is a constant vector. The indefinite integral of a vector-valued function is a family of vector-valued functions differing by a constant vector. Just like in calculus AB, a definite integral gives you a number, and an indefinite integral gives you a family of antiderivatives differing by a constant. So we see that parallel with vector valued functions as well. We'd like to take a look at Objective 2, but before we do that, we'd like to look at a problem from Calculus AB that is like what we want to look at in Objective 2 for vector valued functions. So we have some vocabulary. What is a differential equation? It is an equation that involves a derivative. So for example, a very simple differential equation would be f prime of x is equal to 2x. Now what does it mean to solve a differential equation? If I wanted to solve this differential equation, I can find the function f. That's what it means. So I have the derivative of f, and I want to find the antiderivative, or a family of antiderivative functions. That is what it means to find the general solution of the differential equation. So to do so, you're just going to find the indefinite integral of f prime of x dx, and that would give you the indefinite integral of 2x dx, which is, of course, x squared plus a constant of integration, giving you what we call the general solution, which is a family of functions differing by a constant value. So we did that in Calculus AB. This is called solving a differential equation by separation of variables, but you didn't really have to separate any variables for this particular example. Now, sometimes you're given what's called an initial condition. And if you have an initial condition, you're able to find the particular value of the constant so that the initial condition would be satisfied. And when we do that, we're saying we're finding what we call the particular solution of the differential equation that satisfies the initial condition. So for example, if it is specified in your problem statement that f of 1 is equal to 4, then you would go through the same steps that you just saw, and you're going to make sure that this initial condition will be satisfied. So f of 1 is equal to 4 means that for the function f, when the input is 1, the output is 4. And what we have here is that f of x is equal to x squared plus c. So using our initial condition, we can solve for what the constant of integration c needs to be so that this initial condition will be satisfied. So f of 1 is equal to 4, so you have for the function f an ordered pair xy, 1, 4. So I substitute 1 for x and 4 for y. And when I do that, I get 4 is equal to 1 squared plus c. So 4 is equal to 1 plus c. So c is equal to 3. And I'm able to find what we call the particular solution of the differential equation that satisfies the given initial condition. So I will have f of x is equal to x squared plus 3. This is the particular solution that satisfies the given initial condition. So let me go ahead and see if I can draw an arrow to that. This is the particular solution that satisfies the given initial condition for the differential equation f prime of x is equal to 2x. Having seen that, we're now going to take a look at the vector valued function equivalent of what we just saw. Objective 2, you'll be able to find an antiderivative of a vector valued function that satisfies a given initial condition. So we're looking at example 7. Find the antiderivative of r prime of t is equal to cosine of 2ti minus 2 sine tj plus 1 over 1 plus t squared k that satisfies the initial condition r of 0 is 3i minus 2j plus k. So to do this problem, we're going to begin by finding the antiderivative of r prime of t on a component by component basis. So let's go ahead and look at that. Again, the instructions are find the antiderivative of r prime of t satisfying the given initial condition. So we're looking for a function r of t, and that would be the antiderivative of r prime of t. So we need to differentiate, or we need to integrate on a component by component basis. So we're going to integrate the I component. We're going to integrate the j component function. These are real valued functions. And then we're going to integrate the k component function. And when you integrate cosine of 2t with respect to t, cosine of 2t is a real valued function, and antiderivative of cosine is sine. So you have sine of 2t, but when you differentiate sine of 2t, you will get 2 times sine of 2t. So to compensate for that 2 that you don't want, you multiply by 1/2. And we're going to write a scalar constant of integration. You want to do that for this type of problem, and you will see why when we solve for the particular value of c sub 1 that satisfies the given initial condition. So r of 0 is, you have 2 times 0 is 0, sine of 0 is 0, 1/2 times 0 is 0, and then you get c sub 1, 0 plus c sub 1i. So what do you do now? Again, we're finding r of 0, so we can equate that to the given initial condition r of 0. So substitute 0 for t here. Cosine of 0 is 1, so you have 2 times 1 is 2. So you have 2 plus c sub 2j. So what I said earlier was incorrect. You don't want to equate c sub 2 to negative 2. Instead, you want to equate 2 plus c sub 2 to negative 2. Because we're finding the vector valued function r evaluated at 0, and that will be equated with the given value for r of 0, that is the initial condition. And you're going to do that on a component by component basis. So you're going to equate 0 plus c sub 1 to 3, you're going to equate 2 plus c sub 2 to negative 2, and you're going to equate what we get for the k component to 1. So our next step is to go ahead and evaluate arctangent of t at t is equal to 0. Arctangent of 0 is 0. What is the angle whose tangent is 0 between negative pi over 2 and pi over 2? 0. So you have 0 plus c sub 3, and you're going to multiply that by the standard unit vector k. And again, this is r of 0, and the given initial condition is r of 0 is equal to 3i minus 2j plus 1k. So you're going to equate this with 1. And then you will solve for your constants of integration. So when we do that, we get 0 plus c sub 1 is equal to 3. And then we get 2 plus c sub 2 is equal to negative 2. And then we get 0 plus c sub 3 is equal to 1. So now I get c sub 1 is equal to 3. When you solve for c sub 2 for the second equation, you can subtract 2 from both sides of the equation. You get c sub 2 is negative 4, and c sub 3 is equal to 1. So the important thing is you need to evaluate. So let me summarize the main steps here. Find the antiderivative of r prime of t that satisfies the initial condition. R of 0 is 3i minus 2j plus 1k. So you begin by finding the antiderivative of r prime of t. That gives you r of t with constants of integration for each of the component functions. And then you will evaluate what you've just found for r of t at t is equal to 0 to get what we have on this line. But r of 0 is given. So now you will equate the corresponding components from what you have here to the given initial condition to solve for the values of the constants c sub 1, c sub 2, and c sub 3. And once you have that, you will have the antiderivative of r prime of t that satisfies the given initial condition, and I'm going to write that at the bottom of my screen. So remember that c sub 1 is 3, so I'm going to write, now I'm writing r of t, that's equal to 1/2 times sine of 2t plus c sub 1, which we found to be 3. Multiply that by the standard unit vector I, plus c sub 2 was found to be -4, so we're going to write plus 2 times cosine of t minus 4j, and then we're going to have c sub 3 was found to be 1, so now we're going to have plus arctangent of t plus 1. C sub 3 was found to be 1, so here I have plus c sub 3, now I write plus 1. Okay. This is the answer to the problem. What is this? This is the antiderivative of r prime of t that satisfies the given initial condition r of 0 is equal to 3i minus 2j plus 1k. The problem that we just looked at, and again it is like the AB equivalent that we had gone over before we looked at that particular problem. So that's for objective 2. You'll be able to find an antiderivative of a vector-valued function that satisfies a given initial condition, and when we do that, we say that we're finding the particular solution of the differential equation. So in this lesson, we learned how to integrate vector-valued functions.